Hello, we are Team 1, and welcome to our proposal presentation. Let's start. Our presentation will follow this order. And the paper we chose is Transpose Real-Time 3D Human Translation and Pose Estimation with 6 inertial sensors. This paper was published at SIGGRAPH 2021. As can be seen in the picture below, paper presented a live human motion tracker model with using only 6 IMU sensor. Research on human motion has been actively conducted from the past to the present, and also reconstruction of 3D human motion is crucial for application in various domains. Usually, it researched with computer vision data, but there is some inevitable limit. That is truncation. We can't know true value of unobserved data, so some researchers have tried to obtain plausible value from unseen data, like below paper that proposed model from truncated image. It makes more natural and accurate unseen hand, but it is hard to be a true hand. So we consider the motion capture task using sensor data to be important and chose transpose, which can fundamentally solve this problem. And then what is IMU sensor? It is a device that typically consists of gyroscope and accelerometer. In transpose, they use 6 IMU sensor on left forearm, right forearm, and left lower leg and right lower leg, and head and pelvis as a root. And this is the whole model structure of transpose. It takes acceleration and rotation from 6 IMU sensor as input and return pose parameters and translation. The model is largely divided into 2 parts: multi-stage pose estimation and fusion-based global translation estimation. In multi-stage pose estimation, it is also divided into 3 stages. First stage, it predicts the lift joint position from inertial measurement received as input. And second stage, it predicts all joint position. And in final stage, it uses inverse kinematics for predicting joint rotation. In fusion-based global translation estimation, it predicts global velocity. Before works did not consider body translation because it was hard to predict translation or new sensor value. So transpose defines the foot-ground contact probability, and it makes human motion to translate. And sensor data are sequential, and so models are usually use RNN or LSTM in each stage. There are several related works on human motion capture with IMU sensor. Xsense MBN proposed commercial inertial motion capture system. It used 17 body-worn IMU sensor and fully determined the orientation of all bones of a kinematic body model. And sparse inertial poser, it was the first model that solved human motion with only 6 IMUs, but it used optimization-based method, so only consider offline manner. And deep inertial poser consider real-time with deep learning, but it did not consider body translation, which means global velocity.
Okay, then why did we choose transpose over other sensor-driven motion tracking papers? The 2 main reasons are first, because of its performance and ease of use, and second, its room for improvement. Transpose brought lots of advantages of its predecessors, such as using only 6 IMU sensors and performing it online. But also, it overcame some problems such as translation and computational cost. However, it still had some room for improvement. First, there were motions that didn't work. Motions where the supporting foot moves, but where the supporting foot doesn't move didn't work. For example, skating. Also, their approach couldn't generalize well and heavily relied on the training set. So, if the motion performed was too off from the training set, it couldn't track it. And lastly, even though 6 IMUs were a huge reduction over other papers, it was still too much for daily usage. So, by replicating the advantages of transpose and improving it with a better deep learning model and lower number of sensors, we are aiming to make a daily human motion tracker with smartwatch and smartphone embedded IMU sensors. so that the normal daily people can get better access to this technology. Okay, and here's our plan to do it. First, about how to replicate the previous work. Fortunately, Transpose has its code open on GitHub. So we'll be using its code structure and try replacing the deep learning model and the code for utilizing the data set. And now to talk about which data set we'll be using. So we'll be following the overall process from the Transpose paper. In Transpose, to overcome the problem of having only a small amount of data, they've synthesized artificial IMU data from a motion capture dataset. First, they brought a 3D body model of a human from SMPL and accompanied it with a motion capture dataset called AMAS. And resultingly, they could construct a dataset where a human moves around a virtual environment. And as shown in the two images over here. Okay? And after that, they've placed virtual IMUs on the mesh of the human body. And with the two equations shown in the slide, they've extracted the needed serial IMU data. And here, we'll be replacing the process, replicating the process, but differ the placement of virtual IMUs so that we can get our serial IMU data extracted from specific regions. And
okay, now let me introduce a plan for improving the current model. So the actual plan. So the very first step would be the reduction of the number of sensors to capture the motion. Let me explain why this is actually the improvement. So please imagine the scenario that the one who tries to capture his or her motion using a bunch of sensors. Then the user must properly wear the number of sensors before capturing the motion. Then you might easily find that such preparation steps, again, wearing sensors, can be cumbersome. And furthermore, the number of sensors also can affect the quality of motions, as wearing many sensors can restrict the user's free movements. So I think the one who tries to capture the running motion while wearing burdensome sensors all over the body, then the one must be tired. And this is why we are planning to improve the model by minimizing the number of sensors while maintaining the accuracy. And second, we will try to alter the locations of sensors. So while it may seem unrelated to the improvement, but actually it is connected to the improvement. So currently, the location of sensors are far away from everyday life. Like no one puts something on his or her lower legs as the current model requires. So therefore, we want to make the system more familiar to us and make it fit for everyday use by relocating the sensors while minimizing the number of them and also maintaining the accuracy. For example, many of us are wearing a headphone and smartwatch while holding a smartphone by one hand. Then if these three gears can act as IMU sensors, then the user who wants to capture the motion does not wear any annoying sensors anymore. And finally, the last but not least, the final step would be increasing the accuracy of the model. So for this, we will test the fundamentally different model, for example, utilizing transformer instead of LSTM as shown in the figure. So this is the natural and also necessary step to improve the current model, as you can imagine or just get from the figure. And yes, this is the end of our presentation. So thank you for listening, and please feel free to give any comments, questions, or feedbacks. Thank you.